Okay, good. We are in business. So, good afternoon, ladies. So, I missed the last class. So, my name again, my name is Dr. Faisal Safi. It's written like this. Oops. I usually like my fingers. So, this is my name. This is equivalent to S in French. A-L, okay. That's my first name. Last name is S-A-F-F-I-H, of course. There's a title. We expect titles. All right. And Safih, not Safih in Arabic. You know what means Safih? Crazy. Someone who doesn't know what he's doing. وَلَا تُؤْتُوا سُفَهَاءَ إِيش أَمْوَالَكُمْ. Right? So that's why crazy people should not allow to do anything. Now it's Safih from Safaha. Safaha is Fahu. Okay? Safaha means forgive. Anyways, back to our business. For more information about me, maybe you can check my LinkedIn page. You see my career. I don't like to talk about myself. Without further ado, we go to the syllabus. Very important. You need to read that very carefully. Okay. The course is Fundamental of Microelectronics. You need to have this prerequisite, especially later on when we do circuit analysis. For now, it's okay. If you have any problem, go and refresh. All right. So the first new thing is the team viewer. Now it will be officially used between me and my students. Go and check the team viewer. Team viewer is basically I'll be able to share your screen and you will be able to share my screen if there's any question. Okay. Neat, smart, right? You will enjoy that. Okay. This is number one. Number two. So this is one. Final exam is there. So don't ask that. Now it's up. Oops. I need to bring back the pen. Where's the pen? Otherwise, the smart board will be mad board. All right. All right, smart board. Give us. Oops. Let's see. Ooh. Let me use now the. All right, the mouse. Back to the mouse. Okay, good. All right, good. I'm not going to go through the description. The description is very simple. Basically, we are going to learn three things. We will start with the semiconductors and diodes. Study them very well, how we use them, how they work. Once we learn how the diodes are done and how they work, we go to the next stage. We make a little bit bigger devices, MOSFETs, okay? And then from MOSFETs, we go to jump to another device, BJT. Okay? But these things are related. So if you miss the first, definitely you will miss the second. Okay? So the key point for success in this course is continuous revision. You finish today's class, you go home, relax, take shower, eat, whatever. What did we learn today? Half an hour? Bye-bye. Done. Okay? If you do that, when it comes to the midterm or any exam, you will be extremely ready. Well, the others, they will sleep maybe at 2 o'clock in the morning, you sleep at 10, in excellent condition. Do you understand? Good. So better listen to this. So some of those who did not listen, they suffered. I'm telling you from now, so that you know what I'm talking about later. Okay, great. All right. So it's like a chain. Every single class will depend on the previous one. And I'm not going to do the revision for you. It's your business. It's your job. Do you understand? So you need to do that very, very clearly. Okay, the outcomes are Abbott outcomes. I'm not going to go through them. Read them. They are good for you. All right. Now the grades. Before touch the grades, what we say. The grades are your own merit. It's not a charity. It's not sadaqah from me. Do you understand? I will not support by grades. I support by teaching, by learning. Okay? I may support the grades if I know that students, yes, deserve. And that's based on my assessment. She's working, you know, and I see that. She's proof. I don't believe in words. I believe in actions. Do you understand? Actions speak louder for me. Do you understand? So nobody come and bluff me and say, oh, I'm working hard. No, I see that. Do you understand? Okay. So the grades are your own merit. If you want to get an A, you will get an A. If you want to get an F, you will get an F. Do you understand? So it's not something that is, you know, is on your grip. You can get it, okay? It's not difficult, it's not easy. It's something that you need to work hard. And this course is called Fundamentals. So this is a core thing of electrical engineering program. Okay? The core. You mean the core? Yes. The engine. If you miss it, you miss it. You miss everything else. خلاص? Clear? So that's why you need to put some effort on this. This is an important course. Okay. But it's not something that is extremely difficult. It's very doable, very easy if you do follow what I'm suggesting to you. Okay? Good? So it's not, don't be scared, or those who say, difficult. No, it's not difficult. Who says that difficult is either has problems or they want to make you scared because they enjoy that. And some people, they have this kind of mentality. And that's fine with me. I don't care. But I'm telling you, don't listen to anybody. Listen to yourself. Okay? All right, good. Grades. Very nicely distributed. We have 8 quizzes. Some of you will come later, will say, drop 2 quizzes. That's not guaranteed, 2. Okay? It's not guaranteed we will drop the lowest 2. So do not count on that from now. خلاص? We save some hours down the road. Good. The midterm is 20%. We have 2 class tests. Each one is 10. So they get 20 both. Final is 30. And the project, very short, 10%. Any question? By the way, in my class, you can stop me anytime and ask questions. And there is no stupid question. Okay? All questions are welcome. Okay? Alright? The videos are there. If I say stupid, you will get me in the YouTube. خلاص? Alright, good. So, the second edition is this. And that's what I want to share with you right now. So, I have 2 channels, but I have 2 lists. I have the list one for the previous semester. I didn't give it to the others because they were not lucky like you. You were lucky now. They were not lucky. What can I do? No, it's not that. It's because I didn't learn this until this summer. So I prepared myself. I learned how to do it. Now I can do it in a very quick way. All right? All right, but that's not the end of this. So if you click here, Control click, it will open a browser for you, and you will find this page. This is for last spring term, okay? If you click, please. You can subscribe to get it automatically, but that's the message you will get. The welcoming message first. All right, let me try that. Okay. All right, let me open this. What is that? What's the sound? Can you hear? There's no sound. Where's the sound? My God, it's strange. I have to get somebody. Anyways, the message, I'm sorry you can't hear.
From the computer.
From the computer, are you sure? Let me try that. Okay, let's see. Maybe.
This channel.
Okay, let's do it. I messed with it. It's just 2 minutes, but it's worth it. Why it's worth it? The first page is, you need to pay attention to that one. You see in Arabic, بل السنابل تنحني تواضعا والفارغات رؤوسهن شوامخ. Did you get the message? So, sumbula, you know sumbula?
Yes.
Very good. If it's full of seeds, what does it do? It bounces. Humble. But if it's empty, what does it do? Look at me. So that's what it is. Did you get that? So that's what this, this thing. And that guy, you know this guy, right?
Yes.
Einstein. He just gave another equation. Ego means me. Me, look at me, me. It's 1 over knowledge. So the higher the knowledge, the lower is me. And the lower is the knowledge, you know the rest. The higher is the ego. Very important. Very good. It's good for your life, actually, not only for the course. But I found it inspiring and I wanted to share it with you because I found it useful. So let's hear the message.
My name is Dr. Faisal Safia. I'm a faculty member of the University of UAE University. I am faculty member of the Electrical Engineering Department. Welcome to my course, dedicated to support
is a long course.
I hope my students will learn from it and enjoy it. I'd like also to welcome all the students around the world learning microelectronics who enjoy and benefit from this course. And I welcome all the comments and feedbacks from all of them, wishing them all a good success. Thank you very much for watching my channel and subscribing into it. I'm looking forward to make it even better and to cover more topics, especially in physics, electrical engineering topics, CMOS imaging, and renewable energy, more specifically in photovoltaics, including also image processing. But for now, I'll start with this course, LEC 315, for fundamental microelectronics. I hope you enjoy it and learn from it and benefit from it. Wishing you all the best. Thank you so much. And
All right, that's the first message, the welcoming message. Then later on you will find these courses. So this is just a sample. Last year's week 7, I was teaching a bunch of people there. This one was male class, as you can see. But this is just for the beginning, and then later on I took everybody off. This is one of the students. He's back, but he's not visible there, so it's not a big deal. But later on you will find other, other courses, all the classes you can find there. So there you will find nobody actually. So this is okay. So
good morning, everyone.
all right, that's it. We are without further ado. But if you click on this here on this channel, on this list, we'll find only one. There's nothing there. So basically today will be the video that's gonna be right after the welcome message. Okay? Alright? Why I do that? Why? Let me tell you why. Because I am going to use what's called the blended learning. Where's that blended learning? It's there. I didn't highlight it, I should. Blended learning. So we will blend our learning process with digital combined with in class. Because everybody nowadays like texting and walking and driving and right? All with mobile, yes or no? So you can put a mobile, drink a coffee and see what's going on with this guy teaching us this kind of courses. Alright? Anyways, and the rest will be slides, that's it. That's what I told you. We'll start with semiconductors, jump into diodes. As you can see, it starts simple, like today, and then move on, make devices, and that device we need to know how it works and how we use. Then we go even higher and higher. Oops, is it working? Ooh, no, we'll use this. Then we'll make more complication. So diodes are just 2 junctions. Then we make that bigger a little bit, we make it MOSFET, and then we make it a little bit bigger, and we make it BJT. That's it. And we call it a day, and we call it a semester. That's it. Alright, these are the distributions of the weeks. For each week, what we are going to cover. If you ask me what are the colors, right? Is it like I like drawing? I like art, yes. But this is not art. So this color corresponds to 1 week. This another, this another. We have 3 weeks. See? That's why here you have only 2 colors. So more or less you can expect what you are going to cover each week. So you can go to the textbook and read. And textbook is the main source of this course. Okay? Make no mistake. If you don't bring your textbook, you are in disadvantage. Okay? Do you understand? So our main source of this course is slides, YouTube if you want, and the textbook. We will use the textbook. And I will ask also about textbook issues or problems. Okay? So do not make any mistake. Okay?
So you have to bring it to the class?
Sometimes we can get problems from that, yes. So I'll tell you, open page this, we'll get this example. I know it's heavy. Do your best. Find a solution. Understand? I know it's heavy, I'm sorry about that. If I have the digital format, I will give it to you. But I don't. But I know it's tough, I know. I suffer when I studied too. I didn't have this smart board. We use chalks. So some suffering is necessary to enjoy the learning. Because if it's easy, you will not enjoy it, trust me. Okay? In any ways, do your best to bring the textbook. For the beginning, no, but later on we will use. You can ask the other students, they will tell you the same thing. Okay? So yes, we will use textbook sometimes. But for learning the subject, textbook is primary. We have to. And that's the textbook. By Mr. or Professor Adel Sidra. He is a friend of mine. I worked with him on the textbook. Not exactly the way that we write the textbook, but with other projects. So if you send him an email, he will tell you, I know this guy. Anyways, these are extra reading if you want to go deeper in the microelectronics. And that's it. The dates for midterm and the classes, I will let you know about that. And I will let you also about the quizzes. Okay? I will send you the schedule of the quizzes as soon as possible. Alright, do you have any questions so far about the syllabus? We need to move on. Any question? There's no stupid question, you know that, right? Good. So if you don't have any question, you need to check your syllabus frequently to understand what we are talking about. Alright, good. And if you want to get notification about the YouTube, you can subscribe. Anyways, and you can leave your comments as well. Alright, having said that, we move forward. We start our first class. The AC looks not working today here, huh? A little bit warm, huh?
Yes.
شاونا هذول العيد يعني. We'll have to talk to them about that. Alright, so let's start today's class. Alright, so, oops, now we need to change, let me try. Can we do that? So, I want
So
to...
you can write there and here you can
Oh yeah, it's the, what's that?
you can write there and here you can show the slide.
Sure, that's not bad, not bad. Okay, let's see. Alright, so, anyways, so we'll do that. So if I need to write, I will write like she said on the other side. Anyway, so before we go further, I want you to read this very carefully. Textbook is our main source, okay? And I can change the slides without telling you, okay? Because slides are not the main source. The main source is this, the textbook that we talked about, okay? All right. Because today is a little bit, starting day, so we will use more videos. And this is the first video. What I want you to take from here is many things. First thing, this video will talk to you about a company called Global Foundries. Who knows Global Foundries? Global Foundries is a big player, big fabrication company of microelectronic devices, CPUs and etc., owned 100% by UAE, by your company. So that means if you are lucky enough and if you are working hard enough, you may get a job there. Nobody can tell you no. It's your own, okay? Good. You will enjoy what this company can do. And we will talk about some stuff that we are going to study as well. So pay attention to this video.
You are about to experience a fascinating journey through the clean rooms of the semiconductor industry. See integrated circuits in the making at one of Global Foundries' chip factories. Let our experts walk you through the nanocosmos of the atom. A world that normally remains hidden from our eyes. In the beginning is the circuit diagram.
Oops, sorry. Why does that? Because it touched it. Huh? One second. Let's take all these things out. And then...
You are about to experience a fascinating journey through the clean rooms of the semiconductor industry. See See integrated circuits in the making at one of Global Foundry's chip factories. Let our experts walk you through the nanocosmos of the atom.
Integrated circuit are the name of microelectronic circuit, but very, very
World
small.
that normally remains hidden
That's
from
what you
our
find in the
eyes.
microprocessor.
In the beginning is the circuit diagram. At design centers around the globe, experts collaborate to design circuit diagrams, sophisticated integrated circuits like microprocessors, high graphic processors, and wireless communications ICs. The next step is manufacturing.
Starts from the cement, which we have plenty of it here. Huh?
The
Silicon.
disk substrates for the microchips are made from quartz sand and are called silicon wafers.
I will show you this next class.
To make these wafers, a huge monocrystal is drawn from purified silicon melt. The result is a perfect silicon lattice into which the transistors will later be fitted. However, impurities pose a threat to these flawless silicon crystals. Our global foundries manufacture must therefore take extensive precautions every time they enter our dust-free clean rooms. The result? Our wafers are fabricated in an environment that is more than 100,000 times cleaner than an operating theater.
That's where the integrated circuit get fabricated. I'll show you also
Completely
one of my
free of
visits
dust, the
to a
silicon
nanofab.
discs arrive at the clean room. Here, 25 wafers are packed into each hermetically sealed container and sent off on a journey that will take them through hundreds of manufacturing steps. Photolithographic techniques transfer the circuit structures to the wafers, rather like slide projection. The key to this whole process is a solid mastery of light.
It's called photolithography. He will explain that just briefly.
The silicon disc is spin-coated with a photosensitive resist. UV light transfers the circuit structures depicted on a mask to the wafer.
So the mask is like a film that has the circuit picture.
The exposed
We'll
parts
put
of
it
the
on
resist
the
are soluble and are removed by the
photoresist.
developer.
And they develop it to clean it and just release
The
left
transferred
it only the
structures can
structures.
now be used as a template.
Exactly. So now we
The
do the
protected
doping.
parts of the water surface are etched away. The structures of billions of small current switches are generated on each wafer, tiny transistors. From the photolithographic stage, wafers move on to the ion implantation, where the electrical properties of the transistors will be specified. Here, the engineers make good use of one of silicon's most important properties. Silicon is a semiconductor, which means that its conductivity can change via a high precision and placement of so-called dopant atoms. First, dopant atoms are injected into the silicon structures. These atoms then distribute randomly in the silicon lattice. At high temperatures, the doping atoms become flexible and take on a fixed position in the atomic structure. The complexity of manufacturing tiny transistors requires a clean room as big as 2 soccer pitches. While our people monitor the complex processes, automated manufacturing itself always takes place within hermetically sealed production lines. Copper dominates the next process step. The finest interconnect wires link up billions of separate transistors to form integrated circuits. Before that can happen, however, cleaning is essential for wafers, as particles lurk at every stage in the manufacturing process. Before the copper is poured into the trenches for the interconnects, a barrier layer is applied. It helps to avoid short circuits and guarantees reliability. The trenches are then filled with copper. Finally, the excess copper is ground down to the edges of the trenches. This insulates each interconnect from the others. A microchip made of copper wiring established GlobalFoundries as the first company in the world to adopt copper in volume production. A foundation for the state-of-the-art multi-core processors that GlobalFoundries is introducing today in all product areas. To keep us on the leading edge of the world's chip makers, electron microscopes constantly monitor every step in the manufacturing process, down to the atomic structures of each individual transistor. In 2 months, the wafer is ready. Huge integrated circuits consisting of conductors with a length of multiple kilometers link up 100 billion transistors on numerous levels. And that in a space no larger than a fingernail. GlobalFoundries, the first truly global semiconductor foundry, located in the USA and Germany, Fab 1 in Dresden, and the future Fab 2 in Malta, New York. Together, they'll be 2 of the most advanced chip factories on Earth, and a testing ground for the very latest microelectronic innovations from around the globe. The last production step in microprocessor manufacturing is the packaging of the chips. In preparation for this step, tin silver pellets are applied on the wafer. They will link the chip to the frame. Via the finest saw blades, the chips are cut off the wafer. The flip chip method is used to bond the chip to the frame, which is sealed with a cover.
That's it. So that's what it is. It's a multi-billion-dollar industry, and it's not something that people take it lightly. But it's something that is not that complicated to do. I mean, they did it. Everybody can do it. Anyways, that's a good introduction, and showing that that beautiful company is owned by United Arab Emirates, which is your country. You should really benefit from that. All right. So without further ado, we start. The first step is the semiconductors. That's what we are going to talk about today. So we'll talk about the basic properties. We'll talk about what means doping. It was mentioned in the as ion implantation, actually in the video. We'll talk about that. And we move on forward. We'll talk about later, next week, inshallah, starting drift and fusion currents. Then from there, we start the first important structure, the p-n junction. Very important. This is the first building block, the first device structure that we are going to study, and will stay with us until the end of the course. Until the end of the what? Of the course. If you don't understand it, you don't understand the rest. Alas? Alright, then we do what? Then in this chapter, chapter 1, that's it. So that's basically it. We'll talk about basically semiconductors. Alright? Alright, so Bismillah, we start, and we start by defining what is really a semiconductor. A semiconductor, or some people they call it a semiconductor, is composed of two words. Semi means what? Means half. Yes or no? And conductor, we know the conductor. Yes or no? Conducts what? Charges, electricity. Good. So a semiconductor, or semiconductor, whatever you like to spell, is basically a material that has its conductivity changing. Sometimes it's really good, sometimes it's really bad. So the conductivity changes between a copper property and an insulator like a glass property. Okay? We will see those. Two types of semiconductor. There's a type of semiconductor made out of a single atom. Okay? And then, by the way, also this is part of the introduction. Some things, I don't write them in the slides, but I speak about them. Take notes. Alright? If you mistake a note, it's your problem too. But I've told you from the beginning. Huh? I will not repeat that. Okay? So taking notes is really, really important for you. Alright. So there is a single atom or single element semiconductor like what? Like silicon. Like germanium. Okay, silicon. The code for that, or the node, is Si. Yes or no? And germanium, I think, is a GE, I think, GE. These are two types of semiconductor that are in a material, they are only pure. They have only those kind of atoms. That's it. Either silicon or either germanium. Other semiconductors, they are compound, murakkab, compound of many other atoms. Like what? Like gallium arsenide. Gallium arsenide is basically a molecule, I think A, yeah. Gallium arsenide, AS. Okay? Gallium arsenide is a compound semiconductor. There are many types of compound semiconductors. Okay? It's just to know only. It's not really a big deal, but just to know that we can make silicon, a semiconductor out of single atom, or by combining many atoms to make a good semiconductor. Good? Good. If you have any questions, anytime, stop me. All right, good. All right, where do we go next? Where do we go next? We'll talk about, basically, before getting to those, we get to know these. The covalent bonds. The covalent bonds, so basically, okay, we have, let's say, silicon, okay? Silicon in a crystal, okay? They are connected to the other silicons, yes or no? Each atom is connected to other atoms. By what? By bonds, rawabat. Chemical bonds, and the strongest chemical bond, which is happening between silicon atoms, is called covalent bond. Okay? There are other bonds, chemical bonds, okay? But this is the strongest, and this is the one that is between the silicon atoms. Alright, so what is in this bond? This bond is created by these electrons. These are responsible of creating these bonds. Okay? So in this bond, basically, we have the two atoms comes together. One atom put one electron and the other atom put another electron. And these two electrons, they go around these two atoms, making them getting together. Otherwise, they will push each other. Why? Because at the outer shell of the atoms, we have electrons, yes or no? They can never get closer together. But if they decide to put electrons moving around both of them, they become like one atom, you see? See, you got that? And that's the covalent bond, okay? Very, very important. Very strong, one of the strongest chemical bond that's available, okay? So, but the condition is that each atom will bring an electron, and these two electrons, they will move around the two atoms to create this chemical bond. Okay, good. These electrons, we call them what? The valence bond. Okay? Why this call it covalent? Co means shared. Like cooperation. Cooperation, you see? Cooperation. So together they come and they operate. They share. Good. So that's why they share these electrons. Alright? Good. Thank you very much. That's all what you need to know. Alright, move on. That's what's going on. The silicon, in the outer shell of the silicon atom, it has 4 electrons. Okay? 4 what? Electrons. So it can create how many bonds? 4. Because each electron can be given to the next silicon atom, and we create a bond, and that's what's happening in the crystal, in the silicon crystal, okay? So they create bonds, see? Here 1, 2, 3, and 4. Bingo. Khalas? So these are the bonds that make the crystal, and make a crystal crystal. Do you understand? That's it. So that's what it is. We call this an intrinsic semiconductor, means the property of being a semiconductor is made out of the silicon itself, out of those who are making the crystal. Alright? We call them intrinsic. Let's put it in red. Sorry. Okay? Intrinsic. ذاتية. If you want in Arabic. ذاتية. Intrinsic. Yes?
So if we have a covalent bond, we will have more conductivity?
No, we are not getting there. Very good question. When we have the chemical bond, or the bonds between atoms, those electrons, their job is just to keep these atoms together. They have no business in creating a conductivity. Okay? Those who create the conductivity or help in the conductivity are called free electrons. A free electron. An electron that has no bounding. Free. خلاص. مش مرتبط. Boom. Free. حر. Okay? We'll talk about that very shortly. But that's a good question. So those electrons, as your friend may talk, they are only busy to make the connection between, or the bonds between, the silicon atom and its neighbors. It has here, each silicon has 4 neighbors, okay? Those electrons, they do nothing about conductivity. They help nothing. They don't help in the conductivity, whether plus or minus, nothing. They have only one job, is to keep these 2 atoms together. That's it. Okay? And these 2 atoms together, etc., etc. We'll talk about those free electrons shortly. Alright. We are getting to that answer. At low temperature means at below freezing temperature even. You know the zero absolute degree, yes? How much? How much? Who knows that? How much is the zero absolute? Minus what?
236.
About minus 275, minus 300, okay? Degrees. Because we are talking about Kelvin here. Kelvin is the degree Celsius plus 275. Yes or no? Kelvin, degree, is about the degree in Celsius plus or minus? Plus, 275. 275. Yes, this is
73.15.
73 plus
73.15.
73.50?
Yes. 273.15.
More, but more or less.
Yes.
Roughly, let's put it like this. Make you happy. Okay. Sometimes to make it this one, why? Because the room temperature is basically a room temperature at room. Okay. Is about 300. Just to make the calculation, 300 K. So let's see. C. The temperature at room temperature in C is about 300 Kelvin. That's it, because the room temperature is about 25 degrees, okay? Plus 275, about 300. So here is just an approximation. We're not making too much of mistakes here. Sometimes we do that to make the calculation easy and fast. Okay? Alright, sounds good. So, at very low temperatures, the bonds are okay. The crystal is okay. But as we increase the temperature, what will happen? The atoms will become agitated. Yes or no? They vibrate more.
Yes.
And if you take a wire and you vibrate it more, what happens to that wire? I take it like this. Let's say this is a wire and I do this.
Break it down.
What will happen to the wire? It will break. I remember when I was a child, always like, and it become hot at some point, yes or no? And then boom, it get break. That's what happened with the bones. As you increase the temperature, they break. Okay? They break. So at low temperature, no problem. All the electrons are making the bonds. Everybody is happy. As you increase the temperature, some covalent bonds break because they vibrate. Yes or no? And then when they break, now the electrons, they have no business. They are free again. Now they can go. Now we are creating free electrons. Now these free electrons, if they have a good electric field, they can be moving fine. See? Because their business now not to make the bonds, they are free to move. Nobody, because the outer shell, the electrons at the very outer shell, they don't have strong force to the nucleus. Never. Yes or no? So it's easy to get them out. So it's a good electric field, swipe them away. Okay? Good. So, who did create them? The thermal energy. Because of the heat, yes or no? Without the heat, I cannot do that. So this we call it a thermal generation of free carriers. In this case, free electrons. Good. So, the conductivity at very low temperature was exactly zero because there is nobody that will conduct. But now, as we increase the temperature, we have a conductivity, yes or no? Because we have free carriers. Just I give them some voltage and boom, they can move away. Clear? Good. So the conductivity now is much greater than zero. See the semiconductor? Here isolator. And here is conductor. Yes?
So, doctor, as much as we increase the temperature, as more conductivity, right?
Yes. But once you stop the temperature at a certain degree, we reach what we call, we will get that as well, we reach the thermal equilibrium. We'll talk about that in a second. But yes, the more heat, the more free electrons. Definitely. And it doesn't stop. But then when you break the bond, something happens too. When you break the bond, now that electron can move freely. But when the electron moves away, it leaves behind him a hole. A hole. What is that hole exactly? It's very complicated to tell you about, but you can imagine what I'm telling you. So basically, this electron was belonging to this silicon. Yes or no? That electron has very, very weak force to attach it to the silicon atom. So because of that, for some very weak electric field, because we do have electric field inside the crystal, it can go away. And once it goes away, it leaves behind that a hole. And what is that hole? It's basically a vacancy. There's a place for that electron that it was occupying. That place now becomes vacant. But that place still exists. Okay? That we call it a hole. And why we call it hole? Because, strangely enough, if we present an electric field to that hole also moves. it moves also. That position, it moves. It looks like a positive charge, but there's no charge already. Do you understand? But it looks like that. And yes, effectively, it's like a positive charge. So it's a fictitious, if you will. It's not a real positive charge, but it looks like that and behaves like that. Do you understand? So that's why we call it. It's a fictitious معناته أنه it's like حاجة متخيلة, but it works like that. It looks like that. But what is it in reality? We don't know. Nobody can know. But physically, it behaves like a positive charge moving around. But it's nothing but a vacant position. That's why we call it a hole. Okay? Good. So now, for every free electron, we have one free hole. Yes or no?
Yes.
Electron is negatively charged, hole is positively charged. Bingo. Created by what? By thermal agitation. That's very good. Let's move on. So, as I said, the intrinsic semiconductor is semiconductor that it creates its own carriers by its own atoms. It's not by other atoms that comes to it. That's a different story. We'll get to that. Here, we generated electrons and holes thanks to what? Thanks to the thermal generation, thanks to the heat. So, the generation, عملية التخريج, the way that we create electrons and holes, we call it generation. We generate them by the heat, okay? So, that generation has a rate, has a speed, if you want. How many electrons get created per unit volume, per unit time, okay? That, we call it generation rate. And something more happens. If an electron finds its position, means a hole, they do what we call a recombination. Tick. Now, that electron will not be freely available anymore, and it will be with a bond, for example, or something like that. So it will disappear from the table of free electrons. It will not be a free electron anymore. That's it. It's gone. So we call that process a recombination. It's gone from being free. It now becomes like any electron that creates, that is responsible of any bond. Okay? It will be attached to an atom. So the generation has a rate. The recombination also has a rate. It means how many free electrons and holes they die per unit volume, per unit time. Let's say 1 million electrons, say, get generated in 1 centimeter cubic per second. That's the rate. Okay? We create them over a certain period of time, over a certain volume. Bingo. And why we mention that? Because that student asked a good question. And that good question is this. In thermal equilibrium, when we have a certain temperature, now, if there is any bond that gets created, so we create more, there is also process of recombination to keep the number stable at that temperature. Okay? So they do not get generated over forever, but they do not go down. So at a certain time, at a certain temperature, the numbers get stable. Will not increase, will not decrease. If it does increase, their combination will bring them back to the same level. Do you get that?
Yes.
Clear? So that's what we mean by thermal equilibrium. التوازن الحراري. Okay? That's it. And that's what we meant there. And that's it. So that's it. So this type of generation called thermal generation. There's other ways of generating electron holes by optical, by light, for example. And that's why we have panels, solar panels. Understand? Same story. We create them using the light. You understand? There's other as well, okay? But we are not interested to go there. Now, how many of them per unit time, per unit volume is this? The first equation in your course. So, Ni means the density of electrons, which happens in the thermal generation to be the same as the holes. Because every electron, free electron, we have also free hole, yes or no? So, it doesn't matter here. So this number is for both electrons as well as the holes. The same story. So N means negative. N always means the word negative. Means electrons. I means intrinsic. Because so far we are not using other atoms that are coming from outside. We are using only silicon. So the density of three carriers, whether holes or electrons, in an intrinsic semiconductor is equal to a constant B, and this is the constant B. Boom. Here, that's the number. Okay. Times temperature in Kelvin. Temperature is used only in Kelvin. If you use temperature in C, you are telling yourself, I do not understand you, sir. Give me 0 for this. Temperature is always in Kelvin. Power 3. All right. So, because these two ideas, that it's not good to use the temperature as a way of creating free holes and electrons, and because the number is not impressive, we're not going to use that. So the idea now is to use a different way of generation of electrons and holes, and we call it doping. So what's doping, sir? I'm sure you have watched the Rio Olympic Games for sure, huh? Yes or no? What the Russians did, some of the Russian athletes, what they did? They doped themselves, yes or no? صح ولا لا? They doped themselves. Why? Because they want to be stronger. The same thing here. But in Olympic Games, this is not allowed. So they get out. And they go do something else, not sport. Huh? Here, we dope the silicon with the other atoms from outside. Why? To create more free electrons and holes. So we dope it to make it a better semiconductor. Okay? Good. All right, and for that, so basically we intentionally put what we call impurities, shawa'ib. Why they are called impurities or shawa'ib? Is because they do not belong to the crystal. They are outsiders, strangers, foreigners if you want. Huh? They come into the silicon to change its properties. All right. So we do that purposely. Huh? And why? Because we want to change the concentration. We want a better concentration. Very good. For that matters, we have two types of semiconductors. Because when you dope, it's either you create more electrons or you create more holes. When you create more holes, we created just now a hole by using a dot or an impurity with a 3 valence electrons. That atom could be what? Could be a boron, because boron, how many electrons it has at the outer shell?
3.
3, that's it. So boron is one of the famous doping agent for what? For p-type semiconductors. Now on the other side would be somebody who has more electrons in the valence. So instead of 4, has 5. So the 4 electrons, they will create 4 bonds with others. Huh? And 1 electron extra, I don't need it. I give it to another. Or I don't give it to another. I don't need it, so go away. So it becomes what? Free. And then we'll have created just an electron. So in this process of doping, we created a hole without any electrons, yes or no?
Yes.
So it's not the number of holes, it's not the same as electrons, yes or no? Is the same as the doping themselves, because each dopant will create 1 hole in this case, and here each dopant will create only 1 electron, but the hole is independent of that number. Yeah, the number of free electrons here is the number of the dopant. The number of holes in here is the number of the dopants as well. So it's not equal now. That's why here is a p-type and that is an n-type. Okay.
Sir, so n-type, the conductivity is higher than the...
No. It doesn't mean that. It means only here the majority of a free charge are electrons and the majority here of free charge are holes. That's all what it does. We didn't say anything about conductivity so far. An atom that is also used in this is phosphorus, has 5 charge at the outer shell. Almost there. So this is what's going on. Okay, this is what we were talking about. All right, soon we will close today's class. So just what we said now for the p-type, we said here here. Pay attention. You need to take note here. Actually, the holes in the p-type. You see here, a p means positive charge in a p-type semiconductor is almost the same as the atoms that create them, who are the acceptors, we call them. The boron in this case, okay? Because each boron will create a hole, yes or no?
Yes.
So the number of free holes is the same as the borons. So the density, here we are talking about density, not the number, huh? The density should be number of holes per unit volume, or actually the number itself, but they are occupying the same volume. So the volume, the density or the number is the same of the holes is the same as those atoms that create them. We call them acceptors, because boron accepted an electron from outside to create a hole. Yes or no? We call it acceptor, and that's why N means here the density actually, and A means acceptor. Excellent. The same thing for the donors. The donors, which is in this case the phosphorus, they are responsible about all the electrons in the N-type semiconductor. Okay? Now why we made it almost equal? Why not equal? Because to be equal, I have to write this. I will have to write the same thing here, equal to the donors, plus what? Plus Ni. Because some bonds get broken, yes or no? Some bonds get broken, yes? Thermal generation, yes or no?
Yes.
Yeah, so this is the exact, so Nn is equal to Nd plus Ni. But Ni, the intrinsic density, is actually very, very small. Very, very small. Sorry, the other way around. They are very, very small. So this plus this, So these things are very, very small compared to this. So what do we do at the end? We just ignore.
Doctor, donors atoms mean rejected atom, right?
What's that?
Donors.
No, donors are the impurities that we put inside our semiconductors. Like the boron. See here, remember what we did? Here, remember this? This, here. The donors for semiconductors. They are impurities in the N-type. We call them donors because they donate. They donate electron. They say, I have enough, I have one extra, I donate it for you. في سبيل الله. خلاص? Good? Alright? So we call it donors. متصدقون. The acceptors, they are like beggars. I need electron. So they take electron, they create a hole there. Okay? Okay, we call these guys acceptors. The boron is an acceptor. And we call these guys the donors because they donate. Okay? They give away. Almost there, almost. Let me finish this. But good to ask, The same thing the same equation here, also we can write similar equation there, here. So the holes inside the p-type semiconductor is the acceptors plus the holes created by the broken bonds plus Ni. Yes or no? But this number is very, very small compared to this. Way, way small. So that's why we just say it's too small, so bye-bye. You understand? Alright, almost there. So we finish our class with a few now equations and we're done. This is a famous equation. This is like a golden rule in a semiconductor. If you multiply the density of the holes by the density of the electrons, they are always, whether p-type or n-type, they are always equal to Ni squared. Okay, this is the result. Okay. For p-type, we know these guys, the holes are almost equal to Na, yes or no? So we can replace them with Na, and we can get the electrons in the p-type semiconductor in this case by dividing Ni squared by Na, which is the number of holes in the p-type semiconductor. Okay? So now, if we are in p-type, I can know exactly, or roughly actually, the density or the number of holes and the electrons. This is the number of electrons in p-type. And for this, I know it's Na. That's it. This is an extremely useful formula. Same thing for an N-type semiconductor. I know that the electrons in N-type, they are equal to Nd. So I can know now the holes in the N-type. So just I take this, divide by that, and get this guy. Okay? Very, very simple. Alright, so almost there because of the technical difficulties. This is just talking about what we said, so I'm not going to repeat that. You can read that at home. And that's it for today. Thank you very much. See you inshallah next week. Before we go, I have to take attendance. So